Alan, are you the speaker today? I think so. Oh, you must be Syed. Nice to meet you.
Is that how you say that, Galen? Galen. Okay, that's how I said it. I just wanted to double. I'm so sorry. Yeah.
I was heard it all. I played you. No, as we remember, I think we need to start. How was it time for you? Yeah, go ahead. Good now. So everybody, he's like voting is starting, so you want to proceed. No,
Like momentarily, like just you just got it.
I'm together. So you want to sign it, no, that we should make sure everybody votes only once. Your vote will be on it.
Whatever you are ready. If you want, you can wear this. You don't have to. There's a speaker in the webcam that used to be here. So actually wear this. It's already you don't mind for the students who are. Yeah, let me turn it on. It doesn't get real loud in here. It's really more for the distance people. You can put it in your pocket.
No, what was what? My presentation. Which one? The one I gave one I got from. No, why? Yes. Yes. You're not sure. Are you sure? Yeah. Okay, you're the presenter. I don't. So,
You can just put it on your lapel. This can fit in your pants. Yeah, you just put it on your tie or on your jacket. Oh, turn it the other way. So that might look out. Yeah. Get started.
Welcome everybody. Very good. Syed Alam from University of Missouri Science Technology. Anyway, he's director of Marshall Lab, Machine Learning and Artificial Intelligence for Advanced System. He received his Ph.D. and Master of Philosophy from the University of Cambridge, UK. That's right, that's correct. And prior to Missouri S&T was a researcher at French Atomic Energy Commission, CEA. Which location? In Canada? It's great. So I'll let you go.
I think I had like more longer description. Hello guys. I'm sure that you guys are not bored to see me because you guys saw me like last couple of months ago, right? Like November. So the presentation will be a little bit different, but you'll see lots of like in common. But again, like in the last 4 months, I think 4 months, 5 months, things have changed, but there are some addition to that, and we will actually discuss about that. So today I will be talking about actually the implementation that we are doing in our lab in Martian. A couple of students are working on that, intelligent digital twin, and we are working on that for some funded projects. It will be actually uncertainty aware, intelligent and explainable digital twin, mostly for the complex nuclear systems. And I put the international collaboration because lots of international collaborators are there. So I generally start with my kid, and special thanks to her that actually she's kind of my motivation every day to work. Otherwise, I don't think I would have enough motivation to really carry out the work. And a special thanks to a couple of people. Without them, I believe it would be really difficult for me to actually kind of like the way I'm trying to go. So Dr. Kenny Gross is really a lifesaver for me. Like he gave me his tool algorithms that actually kind of made my life very easy to start. And Dr. Usman, Chakraborty, Prashant, I'm not naming everyone, but those people are basically like really helping me to jumpstart my things. I had my master's and PhD from England, and before that I was in Bangladesh for my undergraduate. And before Missouri S&T, I was in France, as Dr. Kozlowski said, and I'm also a visiting scholar with Rhode Island Atomic Energy Commission. Previously, I was at Korea, KAIST, and Argonne. And before Cambridge, I was in Nonproliferation Network back in Bangladesh, Dhaka. My research thrust is basically we have 3 thrusts. One is intelligent digital twin for structural degradation. Second one is the same technology algorithms goes to the thrust 2 for material informatics. Again, thrust 1 and 2, a lot of components can be used even for cybersecurity, cross-cutting, and system decision making. Although it looks like 3 thrusts, but these are intertangled. So today I'll be talking about digital twin, and that's a humongous thing, right? Like, but obviously I will give you a kind of a broad overview of the components that basically we need to kind of pack together. But but I will give you kind of like a flavor like about that from technical point of view. What is digital twin? Like, how is it different than the high fidelity modeling and simulation? Right, that's the question. Lots of people actually like, I'm reviewing actually UAE, NUP, NRC, and lots of proposals. Actually, sometimes it's not very clear whether it's actually modeling and simulation, high fidelity, or digital twin. There are definitely lots of things that actually make it different, right? So what is that? Digital twin is actually a virtual replica of physical system. That means Syed's digital twin will be a virtual Syed that can mimic, but in the real time with Syed, right? But the virtual replica of Syed should have a temporal synchronization with Syed. It needs to be ideally on the fly temporal synchronization, and we call it in sync. And what's inside that virtual replica that I'll be talking about? So digital twin, as I said, is a virtual representation of the system, but how is it different than the modeling and simulation? One is that it should span, the in synchronization will span over the lifetime. And also, the synchronization of the sensor things ideally should be from the real-time data, like it should be like over the lifetime and updated from the real-time system. And the data you're getting, what you want to do with that? You have to do something, right? So those data you will need some predictive algorithms, and you will leverage that predictive algorithms, kind of make decisions, because you need to use the digital twin for some reason, right? It's not like just I have the digital twin, that's a matter of pride. This tool is mainly for decision making. Like that's the bottom line. And NRC is actually very interested in having a more robust digital twin. And what's the benefits? And basically, they said that according to the NRC 2021 report, that operational efficiency, error, and better prediction, those are the things can be managed well if we can make a really intelligent or uncertainty or digital twin. It's like not all digital twin is going to work yet. And although if you look at Google right now, actually, the key components of digital twin, you'll see long laundry list. Actually, there are only 3 main components. Because I was talking about synchronization, right? For synchronization, what you need? Sensors. So sensors needs to be backed up by instrumentation control. So sensors and instrumentation is actually the first component. Through the sensors, what you're getting data, and how you're gonna do with the data. You're gonna use that for modeling and simulation. So that's the same component. And if you have the modeling and simulation and data and all, you need to have really a database things for data information management. Although the third one, I generally don't cover. So it is actually from the NRC. So it is the NRC recommendation. What should be the component of digital twin? Yeah, the first thing is that nuclear power plant and this guy, virtual, should have temporal synchronization. Then to achieve that, real-time sensor data, right? And you can achieve that through advanced sensors and instrumentation. And you are getting lots of data through the sensors and instrumentation and temporal synchronization, right? And those data need to be through stored in the data information management systems. And then what you want to do with this data? It needs to go to the modeling and simulation part. And that's where actually your informatics things are coming. And this part is actually where my research mostly falls into. And it needs to be through over the system of the lifetime of the system. And then it will help you to get diagnostics and prognostics, operation and maintenance, and autonomous operations. So it has actually lots of functions. So based on your desired thing, you can actually pick the model. And before starting the work, I was talking to some of the colleagues, collaborators, and others, because we are in nuclear field. So aerospace has different type of digital twin, and different industries have different type of digital twin. So I was actually looking at the NRC guideline with obviously collaborators then. What should be the gap? And obviously, the thing is that rather than just doing digital twin work like the way I want, if I know that, okay, these are the gaps from the NRC perspective, and these are the gaps I would like to fill, then actually it's a real contribution, right? Otherwise, this research is not going anywhere. So you're looking at actually a couple of reports from August 22 and from the last 3-4 years, last 2 years, actually they produced 4 reports. According to the report, actually there are a couple of gaps they want to see in the component level. These gaps need to be filled. Number one, data analytics. That means NRC is kind of concerned that there are too many algorithms for prediction. That means too many calculators, right? Which calculator is good? And it's very application specific. And most of the time, people miss one thing, that digital twin is not only about the prediction, it's faster prediction. Because as they say, it's on the fly, right? So do we really have any algorithm that can actually do on the fly prediction? That's actually a big challenge. And I believe at least in nuclear industry, no one really talked about that. And the data you are getting from the sensors, like some are good data, some are bad because of the degradation, some experimental. So how to really fuse that? What are the methods? And you have some noisy data, some lack of data, because you cannot assume that all gonna be picture perfect all the time. And number 4 is uncertainty quantification. Although I separated that, but it should be merged with everything. Uncertainty means over the systems, you are actually having lots of epistemic and aleatory uncertainty from the system, from the model, from your assumption and all. So how to quantify and propagate that? Like quantification is one thing and propagation is another thing, right? And finally, number 5, what makes it really digital twin is basically real-time application on the fly temporal synchronization. And to the best of my knowledge, actually not many people looked at actually that thing in actually the DOE perspectives. And that was actually part of the call this year. And also the prediction algorithm amongst others. Can you really explain that which network or which layer is basically giving the prediction? Because if you know that some prediction is not good, you just don't need to change the model. You see that which layer is actually creating problem. And if you see that, okay, if you remove some layer, you can actually make the machine learning model to explain, right? So that's explainability is actually much needed. So that's going to be actually my focus of the talk. So these will be actually, I will be covering that. So that's one of the proposal actually we are actually developing in our lab. In fact, we published that in 3 journals so far. So it's basically from the real reactor system, you're getting data from high fidelity modeling, you're getting data you're fusing that, and for the data, lots of data are coming, you need some sequential algorithm to get the data, but the sequential algorithm, the problem, like nonlinear Bayesian filter, cannot predict that for the longer term operation. So you have to fuse that with some machine learning model, and then you can get the prediction of your some desired parameter, and that will help you in decision making. So it's just an overview, but I'm going to the detail now. So prediction algorithm, the first thing, that's basically kind of heart of digital twin, because if you cannot predict, it's not going anywhere, right? And my collaborators here from Oracle, IIT Delhi, and Warrants. I'll start with actually 6th grade maths. So you have data, right? And you put that in your Excel file. How to plot that? You can have linear fitting, right? Chi-square based, but it can be, you can it is basically like user defined. You can even have second order polynomial or third order polynomial. The curve can be a little bit different. That means from there also you're actually having some uncertainty. And here actually reliability can be a question, right? In that case, actually grading has been really popular so far, like in the machine learning community and actually applied business community, that if you have the data, it will automatically fit and give you the standard deviation and mean. And also it's basically a combination of lots of Gaussian functions, right? And actually for the mathematical detail, actually we published a paper, you can see the reference. So the mathematical interpretation is there. Now, actually we are working very closely with the MeV performance group. So they want to see that whether the experimental data they have, whether we can infuse that with the Python thing. So we checked with actually thermal conductivity of actually inside fuel to center line, Factorel, and especially we wanted to see that the soiling of CBD6, that whether it works with the creating. That was part of the small project inside. But these are the experimental data mostly. But with that, actually, yes, it actually gives you the result, some prediction. Is orange color, yeah, orange color. But it's doing well. But the problem is that the moment there is no data, it's not really being a gentle. It's actually kind of giving big uncertainty. So that means you cannot assure that every time you will have some data for new material system and others. In that case, actually creating is kind of like as a supervised learning algorithm, it's not really doing it's doing good job, not the greatest job. So the problem is that it's highly uncertain outside of your training data. That means if teacher is not there to babysit, it's not really can do the job. And also the creating's problem is that, not problem, limitation is that it assumes that all data are good. All data are trustworthy. It cannot really define the fidelity. Actually, even you don't have user cannot even define the fidelity. We still did not have the optimization of fidelity, but we define that. But creating cannot do that unless you write a function, which we didn't write. And also for the high dimensional output, creating according to our knowledge, it didn't work well. So we're checking whether multi-fidelity creating can work well. So how physics can be our friend? Multi-fidelity can be physics driven or data driven. Suppose you have some data here, right, up to that point. But up to that point, actually creating is working fine. But when you don't have data, it's just not doing well, prediction. Then again, 6th grade physics, you have some physics equation over the range, right? You're merging that physics and those very sparse data. Actually is doing pretty good job. And thanks to my friend Ben from Oxford, so he actually borrowed this feature from him. So that's the thing actually we will try, that merging physics with some algorithms. So here basically the goal is basically kind of making a synergy between the data and physics. But it needs to be kind of like a sweet. Sweet means when you prepare sweet, you need some salt as well. It's not all sugar, but it needs to be balanced. If sugar is higher or salt is higher, it will taste bad. So data and physics need to have some synergy. So that's actually, but again, the database model have the concern is that sometimes generalization can be an issue. And from there, overall robustness can be a question. And physics-based model, exact physics under radiation environment, we cannot really assure that. And computationally it can be terrible. So how they can complement each other? So there actually we are checking some multi-fidelity algorithms to see whether it can do the work. So on multi-fidelity, we actually published the work with my student. So in the bottom you can see. So where actually we'll assume that there will be some high fidelity data, low fidelity. But we are assuming that high fidelity data will be very few, like limited, while low fidelity data or physics, basically. And this high fidelity will be like obtained through low fidelity mapping, and then we'll be actually multiplying with some scaling factor to scale that. And after the scaling, we cannot even assure that it is gonna really be equal. Then actually you have to add with some discrepancy factor. It's kind of an automatic function. And high fidelity is generally a validated experiment, and it's very expensive to get because it's like lots of sophisticated experiments. But low fidelity generally coming from some PDE and ODE solution. It's fairly easy to get, but again, it's approximated behavior. So we wanted to check again with the Python team what's going on, right? So we checked that, okay, this is uranium silicide thermal conductivity. Suppose there is 50 data points. But if there is something that we have only 7 data points, how it will look like? So it's actually not really doing good. It's actually pretty bad. And we published actually a paper on that. That is actually not predicting well. It's actually completely like quickly and those. Then actually, as an approximate equation or a low fidelity equation or low fidelity data, we actually incorporate the physics from the Joshua Taylor 2015 paper, like published in Journal of Nuclear Materials. And after that, actually, we have seen that, okay, this is actually predicting pretty well. Obviously, there are some uncertainty, but still, it's better than that, right? Like, better than that. And then actually, swelling is actually kind of like a different beast because swelling is actually like differential swelling, like temperature dependent gradient and strain and all these things. So Python team is actually a little bit actually like curious to see that whether swelling also works. For swelling, it's even worse. There are 80 data points for swelling for prediction. But when we actually got 7 data points, this is that bad. So you can say that why is that bad? Because our objective is to generate the prediction from the lowest amount of data. Because if you have lots of data, if you have just 50 to 40 data and then predict, you cannot take the credit. You have to make sure that you are generating the prediction with the lowest amount of resources you have, right? Then you can say that, okay, I achieved it. And these 7 data points prediction is even worse. That's what actually Python team wanted to say. But when we have this actually approximate equation, it actually predicts not that with bigger uncertainty, but we actually made that we predicted the model with very small data point. But if we improve the data points, high fidelity data points, experimental data points, uncertainty will also change with actually like the more data point with the from the experimental side, the less uncertainty. But when you do this step, you have to make sure that your model also can support with the minimum number of data. Otherwise, the model never can be generalized. Because the idea of those technologies that it needs to be generalized. However, multi-fidelity fielding is good. The problem is that in material systems and those kind of things, you cannot assume that all data you're getting have some correlation, right? Like, even if you get the case that there is no correlation or pure correlation established, what's going to be your way? Right, because that's the question we got from Oracle, that say you're assuming that all going to be nicely correlated and you're just plotting it. Suppose there are some new material system that we're planning to see, and there's no correlation developed for that. Can you really capture the correlation? Good question. So they are actually like, we are working on that, and here actually, we are thinking about physics-informed neural network, and we tested physics-informed neural network, which is actually fairly a big buzzword now, but it just didn't work for us. Like that's the report we gave to Oracle and Python team, Idaho Advanced School Revision team, that it just didn't work for us. So, but if we actually use the same technology, multi-fidelity kriging, this idea, and throw it here, it somehow works. So it's actually a multi-fidelity composite neural network. We will be assuming that a small set of high fidelity data, take a small. In all our cases, we will assume that a small set of high fidelity data is there, and lots of low fidelity experiment or equation or data are there. And also we need to come up with a model that can dynamically learn the correlation. Like you know that there is a scheme, right? Generative GAR or those kind of scheme is there to capture nonlinearity. Right? So these kind of non-linearity, can we really learn the correlation? And can we capture the physics that is not there in the material? And can it work in multi-scale material environment? Because making things work in actually macro scale is, I believe, is fairly straightforward sometimes, but not in the micro or the meso scale, especially for composite or those kind of things. How actually can like work, right? So this is actually one of the things actually we modified the model from one of our Brown collaborators. So it's actually multi-fidelity, but we cannot assume that it's going to be all linear. So we are actually dividing the network to the linear system and non-linear. So the basic idea is basically you have some low fidelity data. You just put it through the low fidelity network, and you get the low fidelity output and fuse that with the high fidelity input, like some experimental data. And there is, you have actually also linear network and nonlinear network. By optimizing your regularization function and those relaxation parameters, you basically combine that network. And actually from there, actually it can, but again, by optimizing your relaxation parameter, actually these two networks actually can learn the linear and nonlinear correlation between the high and low fidelity data. And just to make sure that actually in the linear part, we don't have any activation function. And in the nonlinear part, we use actually a hyperbolic tangent function. And with the learning rate, we use actually 0.001. So here actually, again, with the Python tool, because that's what I'm probably working, they wanted to see CBD-SIG, whether they can work. If you actually work on Python, and if you see the silicon carbide material model inside Python, like there, that's the equation they are using. In fact, people are publishing with that model for the rest of the whole temperature region. But the problem is that this gentleman only works for 1073 Kelvin. After that, there is no physics or correlation known. Right. So the idea is to get the correlation out of that. That means if the point in the points into the defect swelling, you know the thing, but not in the void region. So that's actually we need to get the correlation that how to extend that in the high temperature region. So we actually checked with the network, different layers and neurons and see that where actually it merged well. So generally 20 neurons and actually 4 layers where actually we got actually all these really converged. One of the things actually we really also Python team and we also wanted to see that this point, high temperature and low temperature inflection point. Can you really get the inflection point? Because that's where the transition occurs. So actually we got the actual inflection point through actually like some optimization study, and actually you can see the results here that we can get. And also from this study, we can get the correlation that, okay, if you have the low fidelity answer, then actually with the temperature and others, you can get the high fidelity. So the details of that actually is just accepted. It's not preparation, it's just accepted in Nature Computational Materials. I believe after a couple of months, it will be online. We also wanted to see that when you have less amount of data, can we really still predict that? Suppose in the previous model, we used actually 20 high fidelity data. Then actually we check with the 7. Although it looks good here, that okay, smoother is better than Gaussian and multi-fidelity. But in terms of result, it's not amazing. Still, there are room for improvement, and we're kind of stuck that how to improve that. That means when it's scarce, it's kind of like we are kind of like stuck. Like we are really need to work on that. And if you guys have idea how to improve that model, I would welcome that. So again, this multi-fidelity neural network, the problem is this gentleman inherently has some induced bias. And also, we are checking that in multi-scale environment. In multi-scale, actually, it's like not amazing. Like it fails sometimes. So the idea of having generalization really did not occur here, honestly. Actually, and that's the actually comment we got from Nature Material Physics, material computation, that they accepted the paper, but we have to make sure that okay, in those areas it doesn't work. So that thing we did not mention. That's what they wanted us to make it very clear in the journal, and we are working on that. So another technique we came that neural operator. It's not actually your traditional neural network. In neural network and those things is basically a vector multiplication or those kind of things. You have done vector thing in paper, right? It takes time. Just go around class, right? But when you have the functional approximation, it's pretty fast to put the number, result is there, right? And this neural operator, what it does is out of distribution generalization, that means unseen radiation environment can be captured. Accuracy might be an issue, but we'll talk about that. Out of distribution generalization, because that's the thing you want for your digital twin, right? Out of distribution. And also, can it really capture the unseen environment, obviously based on the previous thing? And a small generalization error. Right. And for that, actually, you have to take a different approach. And this neural operator thing is still like you need lots of data. But again, we already established the fact that multi-fidelity neural operator or multi-fidelity approximation can work well. But the best thing that came out of that for faster prediction, that's actually like very helpful. It actually can give you 30 times more like faster prediction than MFNN with the same accuracy. And I believe for that reason actually, I think it was invited to NUP, a part of the proposal, that faster prediction for the digital twin. So just a basic idea. So when we actually do the like a regular digital twin for like prediction model analysis, we assume that okay, there are some input, and for the output, there are some boundary condition. You train the model, you get the output. But in real environment, suppose you are bringing microreactor conditions, microreactor and others. So there will be like over the lifetime, there are lots of boundary conditions, lots of changes in parameters and others, right? So that means the prediction you are actually getting without considering that is not really flying anywhere. Like it's not really the accurate one. Suppose you get, for example, pitch to diameter 1.33, you can go forward with that. It's good, but it's not the generalized one. So in that case, actually, for example, over the time you have 100 patterns or 1,000 patterns. That means you have to build 100 or 1,000 models. You have to train the machine learning. It's not good, right? It's like it's not good. It's not going to work. So their actual operator learning framework actually works well. And actually, our paper you can see actually Google actually is accepted in engineering application of AI. That how operator learning can be a viable option for the digital twin prediction and faster way. Also, so I'm sure that you already know about the surrogate model, and those actually we use actually the kind of these things. You have the input data, you run the physics model, you get the physics data input and output, and run it in a surrogate model, reduced order model, and then whenever you need the input, you just call that and you get the output. That's basically the overall idea of the surrogate model. Now, we wanted to check with the real digital twin things, sensors and others. Obviously, we did not use the real sensor. We assumed that from the sensor some data came. So you have some sensor, a fixed sensor point, and from the fixed sensor point, you have some data. And also, we are assuming that in the random location, you have some actually sampling position, output, and others. And then we actually use actually rather than regular neural network, we use actually two networks, branch and trunk. Branch will take actually fixed sensor data in the discrete point, and trunk will take actually domain of the output functions. That means sampling position in terms of output and all. Then actually it will have a dot product and we'll get the output. So there are two references on that. You can see the more detail on the mathematics and all. And we wanted to check that in the more generic thing in diffusion reaction system, that actually like we have input function from the fixed sensor position, and it is actually the sampling position. And then but we trained it with equal like xi, aej, and others actually like ran them with like lots of data points. Actually. We tested actually a finite difference method using fast Fourier transformation. Is from the simulation and is from the neural operator prediction. So R square is actually pretty accurate, around 99%. And we want to test it with actually some Monte Carlo method. So it's like we have the air and concrete and some source, neutron source. We actually trained 1900 patterns for that, and using Gaussian distribution. And this is actually speed simulation and it's actually deep neural network prediction. The good thing that happened is that in the 10 CPU code and 20 threads, like 10 CPU, this one fit simulation is actually MCMP equivalent, 33.9 seconds. And if you really train well your neural operator with 1900 patterns, it will take 0.003 seconds. So accuracy still needs to be improved, but the faster thing that we achieved, and actually it was invited to NUP, but we have other plans to actually expand that in different directions. And uncertainty quantification. So you know that in uncertainty and others, generally you have the fixed point, input temperature and others, but then you get the fixed output, right? But if you really want to get the uncertainty, it needs to be distribution, right? If its temperature is 500, it needs to be plus minus 5%, right? To get the distribution and moment. So generally, our team developed actually polynomial chaos method, where actually you have the randomness with the input parameter, then randomness will be converted to the polynomial approximation, and this polynomial approximation will give you the probability distribution function. From there, actually, you get the standard mean kurtosis. You don't need to go to kurtosis. You don't need third order moment, but standard and mean deviation will generally give you the uncertainty. And I have actually around 15 papers on uncertainty quantification. So I put 8 only. So you can check that actually it's there. And actually, again, with the Python team, they also wanted to see some uncertainty quantification. So it's actually kind of, we took the 4 input variable and wanted to see that with the 4 input variables uncertainty, what's going to be the output look like. So we checked actually 4 input parameters. It can be 4 or 40 because the model will be expanded. Chaos order can be expanded. And we got the actually from from the MCMP or scale, we got the MCMP, we got the power history and linear power, and we got actually 5% of uncertainty for now, and got actually PDF of the input with the randomness. And then actually from the probability distribution function, we actually got